The word laser is actually an acronym that stands for Light Amplification by Stimulated Emission of Radiation. A laser is a device that emits a very special light through a process of optical amplification based on the stimulated emission of photons, which are small amounts or quanta of electromagnetic radiation. Laser light is very different from normal light. The light released from a laser is always monochromatic, coherent, and directional. Recall that monochromatic refers to light containing a single wavelength that corresponds to one specific color or frequency on the electromagnetic spectrum. That coherent means the light is organized in such a way that each photon moves in phase with the next, and that directional means the light is very strong and concentrated. A prime example of non-directional light would be that of a flashlight, where the light released is very weak and travels in many directions. The principles of laser operation are largely based on quantum mechanics. Lasers operate by the constant emission of photons, in which there are two types: spontaneous emission and stimulated emission. Spontaneous emission occurs when an electron is excited, meaning it is at a higher energy level than normal. This electron will not remain excited forever, and when it spontaneously transitions back into an unoccupied lower energy level, the electron will emit a photon. A material with many atoms in an excited state may thus result in radiation that is very monochromatic, but the individual photons would have no common phase relationship and would emanate in different directions. Therefore, spontaneous emission is not useful when trying to produce laser light, which again must be coherent and directional as well. However, stimulated emission can produce light with the specific properties required in a laser. Stimulated emission requires an incoming photon and an electron in an excited state. The photon must possess the amount of energy exactly equal to the energy difference between the two levels of the targeted electron. This incident photon can trigger the transition of the electron back to a lower energy level, inducing the emission of another photon. This photon is called a twin photon, as it is an identical copy of the incident photon, with the same wavelength, same direction, same polarization, and same phase. These two photons will continue to travel until they encounter more excited electrons, in which they will induce more emissions of identical photons. Every time this process takes place, the amount of photons will double. This chain reaction produces many coherent photons that will propagate in a very specific direction, producing a special type of light amplification that explains why lasers emanate monochromatic, coherent, and directional light. In order for this chain reaction to continue occurring, the electrons must return to their excited states after emitting the identical photons, so they can emit more and more. If the electrons are still at the lower energy levels when the incident photons come back, the photons will be spontaneously absorbed, and the reaction will stop. In order for the electrons to constantly return to the excited state, population inversion must occur. Under normal conditions, more electrons are in a lower energy state than in a higher energy state. Population inversion is a process that aims to invert this by achieving more electrons in the higher energy state than in the lower energy state. In order to achieve population inversion, the laser medium must be supplied with energy. The source that supplies this energy is called the pump source. Different pump sources are used for different laser mediums, and some of the most common population inversion methods include optical pumping, electric discharge, and thermal pumping. In optical pumping, light is used to supply energy to the laser medium. An external light source, such as a xenon flash lamp, is used to produce a higher population of electrons at a higher energy level. When the light source provides enough energy to the lower energy state electrons in the laser medium, they jump into the higher energy state, E3. After a very short period of time, they will fall back into the next lower energy state or metastable state, E2, by releasing radiation as energy. The metastable state, E2, has a greater lifetime than the ground state, E1. Hence, more electrons are accumulated in the energy state E2 than E1, and thus population inversion is achieved. Electric discharge refers to a flow of electrons or electric current through a gas, liquid, or solid. In this method of pumping, electric discharge acts as the pump source or energy source. A high voltage electric discharge is passed through the laser medium or gas. The intense electric field accelerates the electrons to high speeds and they collide with neutral atoms in the gas. As a result, the electrons in the lower energy state gain sufficient energy from external electrons and jump into the higher energy state. The last main method of pumping is thermal, where heat acts as the pump source. When heat energy is supplied to the laser medium, the lower energy state electrons gain enough energy and jump to the higher energy level.